From the first talk in this series, it's clear that soil pH is a very important property. And the main reason it's important is that it affects the availability of particular nutrients. Soil pH affects the availability of particular nutrients to the plant. This is because the chemical form of a nutrient that is present in the soil can change due to the soil pH. This graphic here shows that between 5.5 and 7, most of the nutrients and other ions in the soil are present at relatively high degrees of availability. But as the soil pH drops, what we see is that there's a decreased availability of nutrients like molybdenum and phosphorus, sulfur, boron, selenium, and also the cations such as potassium, calcium, and magnesium. There's also an increased availability of aluminium, iron, copper, manganese, zinc, cobalt, and nickel. And all of these nutrients can become more available, but they also become so available that they can end up becoming toxic. One of the features of iron and aluminium is that they strongly react with phosphorus, and so can precipitate into insoluble compounds in acid soils. These compounds are iron and aluminium phosphates, which tie up phosphorus in a form that is unavailable to plants. This is often measured using a phosphate buffering index, or PBI, which describes how strongly phosphorus is tied up, and it's also known as fixation. Normally in our alkaline soils, we have a PBI of about 100, but on acid soils, there can be very high PBIs, 400 and above. An example of the soil test showing PBI results is given at the bottom of the slide. The graph at the right shows that phosphorus is fixed with iron at a pH under about 5. Phosphorus also precipitates with aluminium at pH between 5 and 6, and that phosphorus is most available to plants between pH 6 and 7. Aluminium in its own right is also toxic. It's species and cultivar specific, so different crops have different responses. In the graphic here, at pH 4, where the soil hasn't been limed, you can see the degree of root pruning that's occurred due to the toxic effect of aluminium on the root tip. At 1 tonne per hectare of lime, raising the pH to 5.1, the aluminium level declines to 2 parts per million, and you can see the change in the rooting system. Legumes are generally less tolerant of low aluminium, and in this case, the cereals are also quite intolerant of acidity. When you get your soil test, as well as pH, you'll often have an exchangeable aluminium content. Because not all acid soils have high exchangeable aluminium levels. So in your soil test, it's important to look for pH and exchangeable aluminium when making species and crop selections. Manganese is another nutrient that's required by plants, but it can become toxic in autumn and in late spring. Over summer, manganese in the form that is available for plants to use increases as it is produced from unavailable forms of manganese. It can stay at quite high levels in the autumn, and at sowing time, it's taken up very rapidly by the crop. So we can end up with manganese toxicity symptoms, such as what we see in the canola and peas in the 2 pictures on the slide. Manganese toxicity is lower in the winter, but it can also occur in the spring if there's waterlogging, as this causes soil microbes to convert unavailable manganese back to available manganese. Molybdenum is also strongly affected by soil pH, so much so that a 1 pH unit increase changes the availability of molybdenum 100-fold. There are a few problems with molybdenum above pH 5. The main problem with molybdenum is with legumes. It's because the rhizobia that are present in the nodules of the legumes use enzymes that contain molybdenum for nitrogen fixation. As a consequence, it looks like nitrogen deficient because in fact the plant is starved because it can't fix nitrogen. But the issue is not so much nitrogen, but a deficiency of molybdenum, and molybdenum uptake can also be affected by high sulphate levels in the soil. Calcium is one of the nutrients that declines in availability with soil pH. Calcium deficiency is not a common issue in field crops, but we sometimes see it in canola in the spring as wither tip symptoms. Where there's low availability of calcium, it's more a transport problem than a supply issue. It often occurs in overcast weather where there's little transpiration inside the plant so that calcium's not moving to the growing plant tissue. Research has shown that there's little response to applied calcium at this stage in the crop. While low pH and progressive acidification of agricultural soils is a very significant issue, it is one that can be managed. With all these nutrient and pH interactions that we've discussed, the judicious use of lime and so raising soil pH will help avoid those crop and pasture problems. Liming is the key strategy to make and keep acid soils healthy and productive.